Hello. So what I'm going to do in this video is to review, to discuss the dummy variable trap, which was question 6 of homework 1. So I did not explain much about the dummy variable trap, but I realized, as I expected, it was not easy. By the way, for the other questions from question 1 to 5, I believe it is not that difficult, just as a matter of your mathematical writing. And if you read others, your friends' answers, then I believe you can learn from theirs. And also, I commented carefully in detail on the answers, so I believe they are not a big problem. But question 6 is unique and quite different. So let me do some additional lecture on that. So dummy variable trap and so by the way, so dummy variable and interaction terms, the main topic of this lecture is on dummy variables and interaction terms. They are very important in practice. So theoretically, I'm introducing them in the chapter of multicollinearity, but actually they are important on their own right. So you can think it as an extra lecture. Okay. So let me think about simple example. Y is wage, whatever. It's not important. Y is an outcome, and we will consider two dummy variables. M stands for male, F stands for female. So M takes 1 or 0, and also F takes 1 or 0. So F is female indicator, M is male indicator, right? And if you set up regression equation like this, I believe you know this does not work because there are 3 regressors, 1, M, F, but you know the multicollinearity arises if you can make this equality for some A and B and C. It is possible if you plug in -1, 1, 1. So you know M plus F always equals 1. So that means -1 plus 1 plus 1 will make 0. That's the multicollinearity, definition of multicollinearity. So this is the mathematical definition. Okay. So then another way to think about this is, what I recommend here is, if you only have dummy variables, you can think it as group-wise averages. Simply in this regression, what you are doing is your sample is divided into male and female and analyze their difference. That's what you are doing. So basically, the information you have can be summarized into these two group averages: female average, male average. And in this model, if you write this model, right? So because of this multicollinearity, I decided to drop M. And suppose you have this regression model. And then in this case, if female, F takes 1, so the regression captures the female average as alpha plus beta because F takes 1. But for male, F takes 0, so the group average, male average, will be simply alpha. Because this part is 0, so this term will disappear, right? Of course, the error term will disappear because when you take expectation, the expectation of error term will be 0. So then, again, female average is alpha plus beta. Male average is alpha. Then in other words, the parameters capture different things like this. Alpha should be interpreted as male average, and beta should be interpreted as the difference between female and male. In particular, you subtract male from female. So we say male is a reference group. So male, the intercept captures male average, and beta captures female premium. If it's negative, like negative premium, right? So the reference group is male, and the reference group coincides the dummy variable you dropped. Because you dropped male indicator, that becomes the reference group, and intercept will absorb the reference group. Okay. You can see the same same thing if you drop the other indicator. If you drop F, then also you can think about this regression, which is working, and the difference is now intercept captures female average and male average is captured by alpha plus beta. So the interpretation should be different. That's the point. Now you have to interpret the intercept as female average, and beta is the difference. Difference is the same, but what you subtract from what is different. You subtract female from male. Previously, like exactly the roles of male and female switched. Like flip the role of male and female, right? So this is very confusing, but simple enough, right? Easy to understand. But first, you have to tell if there is multicollinearity or not. And if there is a multicollinearity, you have to drop something. And what you drop will become the reference group. But if there is no multicollinearity, you can estimate that. But you have to think about what those parameters capture, right? Like this. So, and thinking about group level average will help a lot to interpret the parameters. Model 3. This is interesting. Rather, you may drop the intercept. You can drop the intercept and keep two dummy variables. This is also possible. When you drop the intercept, they are not multicollinear anymore because multicollinearity is possible only when you have 1 here. So it is not 0, but 1. So without this part, M and F cannot make 0, right? So this is also working. In this case, it's more simple. So alpha captures female average, beta captures male average. So when you compare these three different working regressions, the interpretation should depend on what you drop, right? In this case, there is no reference group, but there is no difference directly captured by the parameters. So then, no, it doesn't matter whatever you use. All the three models are mathematically identical. So it's not a problem, but one model may be more convenient than the others. For example, if you want to capture premium like this, then this model will be the best, most convenient, because you can directly estimate that parameter. But if you wanted to capture the premium this way, difference in this way, then this model will be better. But if what you want is not the premium, not the difference, but just group-wise, two group-wise averages, then this model is the best. So depending on what's your parameters, one model may be more convenient, computationally more convenient than others. But in the end, it does not matter. Still, even if you estimate this model, still you can calculate the difference between them. That is possible, but the main problem is calculating the standard deviation. Calculating the standard deviation is a little more complicated, but Stata has built-in function for that, built-in command for that, but that's just extra step, unnecessary extra step, which can be reduced if you used a different model. So now I will, in the same model, I will add age dummy variable. Like simply, A stands for old people above 40 years old, and B stands for younger than 40 years old. So A and B are another dummy variable, but it's a different dimension. So we have male, female in one dimension, and old and young in another dimension. So it's 2x2 categories, like as you can see here. So then you can think it as 4 different groups in your sample. So what with these four dummy variables, M, F, A, B, four dummy variables make up four groups, but the groups are defined this way. I will simply call them in their 40s, 40 years old and 30 years old, right? Simply. So you have to think about these four groups. Now you have to think about multicollinearity and how interpretation of the parameters. For example, so think about this. Include all the dummy variables, four dummy variables, and intercept. Obviously, it does not work. First, there are 5 parameters from 4 groups. The information you have are basically the averages of 4 groups. There are 4 group averages. That's the key information you have from the data. But there are 5 parameters, so that you cannot handle this equation. Or more rigorously, there are 2 multicollinearity problems. First, MF intercept. So you have this multicollinearity between M and F and intercept. Another multicollinearity from this pair, A and B and intercept. So clearly this regression is not working. Now, then if you drop one variable F, so then first the number of parameters equal to the number of groups. In that sense, this intuition does not work here. Still, multicollinearity exists between A, B, and intercept, right? Even if you drop one dummy variable to match the number of parameters and number of groups, still the problem exists. So what I'm telling you here is, this intuition is correct, but it does not guarantee identification. If this condition fails, identification fails. However, even if this condition holds, that doesn't imply identification holds. So it is just a necessary condition, not sufficient condition, right? So more rigorous way to show identification is using the definition of multicollinearity, right? So even if this is true, identification fails. Similarly, the same thing happens if you drop intercept or another variable. So dropping one variable does not help because there are 2 multicollinearities. There are 2 multicollinearities, so you have to drop one from each group. By the way, then you may wonder why this equation has multicollinearity. Like here, if the intercept does not exist, then there is no multicollinearity between F and M. Then how can you interpret this? In this regression, the multicollinearity is M plus F equals A plus B. Without intercept, still, like let me show you. Oh, sorry. So you can say the multicollinearity is coming from this equation, right? So this is the proof of the multicollinearity in this regression equation. So it does not work either. So then I will show you the working model. This is the correct working model. You have to the most general working model. There are 4 parameters: alpha, beta, gamma, delta. And what's interesting here is the key point is the interaction term. You have to interact between 2 dimensions, like age dimension and gender dimension. And then by doing this way, you can represent the group averages using 4 parameters, right? So female 40 years old will have 1, 1, 1, 1. So alpha, beta, gamma, delta. And male 40 years old will have 0 here, 1 here, 0, 1. So this will disappear and this will disappear. So 0 here, 0 here. So these 2 terms will disappear, and in the end you only have alpha plus gamma. Similarly, female 30 years old. This is 0. This is 0. So alpha plus beta. Male 30 years old, we'll have all zeros, 0, 0, 0, 0. So simply alpha. Okay? So then also you can think about this. Here, from each group of variables, I dropped male from the gender group and I dropped young cohort from the age group. So as a result, this group becomes the reference. I dropped man 30 years old. So that is the reference group, and this will be absorbed into the intercept. Intercept will take care of this group, right? So all the four groups are well represented. And from this information, you can go the other way to represent the parameters. So right, from this information, you can interpret alpha is the reference group's average. Beta is the difference across male and female in these two groups. The difference between these two groups. So you may interpret beta this way. Beta is the female premium among 30 years old. Right? Right? And gamma is the other dimension. Difference in the other dimension. Gamma is the difference between 40 years old and 30 years old for men, among men. So gamma is age premium among male, right? So comparing these two groups. Then finally, delta is tricky. Delta is tricky, but after simple mathematics, try by yourself, you should be able to interpret this as, isolate this as how the female premium differs at different ages. Put it this way. Female premium was beta among 30 years old. But among 40 years old, the female premium is beta plus delta. So difference between these two groups. So female premium is beta plus delta for 40 years old and beta for 30 years old. So your interpretation is that delta is the difference in differences. Difference in female premium across age groups. Okay? Right? One female premium and another female premium and compare them, that's delta, right? So we call this difference in differences. Alternatively, equivalently, mathematically, you can just subtract and add the same thing and rearrange terms. Then you may put it this way. Age premium differs between men and women. So for men among men, gamma is the age premium, right? When you get older, wage increases by gamma. But for women, your wage increases by gamma plus delta. So delta is the difference between men and women in their age premium, right? So just you are changing the role of the dimensions, right? So take difference this first and then take difference there. Or this difference first and this difference later. So think about this, and this is an interesting parameter, and that is the role of interaction term. Interaction term literally interacts across dimensions. You have two dimensions, then the interaction term will handle the interaction effect, right? And multicollinearity 5. Now I'm tweaking the equation to a more complicated case. Now you interact like this. Then, so still there are 4 parameters. So number of parameters do not cause any problem. But the problem exists because this f equals f times a plus f times b, right? This is the multicollinearity. Multicollinearity is coming among these these 3 variables. So in this case, f plays a kind of similar role as the intercept, right? So women can be divided into 40 years old women or 30 years old women. So in that sense, they are multicollinear. Or even more strange regression equation. F times B, F times A, F times B, M times A, M times B. This is actually pretty good. It's working. It's working. Try to find if there is any multicollinearity relationship. No, because exactly one parameter corresponds to one group. So F times A is 40 years old female. B times F is 30 years old female, 40 years old man, 30 years old man. So alpha, beta, gamma, delta corresponds to a single group average. So this model is working well, general enough, good. And another model. Think about this: F times A, M times A. Check it if it works. Yes, it's working, and try to find out how those four parameters correspond to the group averages. A simple exercise, interesting exercise. I believe you should be able to do this. Like you can change the model as much as you want. I don't know how many combinations you can make, but whenever a model is given, you should be able to test if it's working or not, right? And by doing this, you can get the correct interpretation of the parameters, right? Try and see what kind of models you can use. Also, commonly used models are usually in this form. Usually we don't care much about interaction terms unless they are particularly important. So when the interaction term drops, that means delta, we are assuming delta equals to 0. So then the assumption you are making is that the age premium is the same for men and women, or the female premium is the same for 30 years old and 40 years old. So this is another way you can utilize the interpretation when you understand the model. Even if there is no intercept in the regression equation, but you have to see the hidden information, hidden assumption here. The hidden assumption is this, right? That's the hidden assumption. And so understanding the general mechanism of the interaction terms and the dummy variables is important. Okay. So actually, question 6 of our homework, I added one question from last year. We have these two relationships. So this will be the main source of multicollinearity. And now you have to think about 9 groups. So like 2-dimensional, but 3x3 model. So you have to think about 9 different groups. If possible, write down all 9 groups and like derive the one-to-one mapping between the groups and the parameters. It will be an interesting exercise. So if you have this model, the multicollinearity is coming from this part. So T is dropped, correctly dropped. Trucks are the reference group from this group of variables. However, this part causes problem. The nationality causes still the same problem. So you have to drop another variable from one of these variables. So for example, if you drop J, then you have this regression. So then there are only 5 parameters for 9 groups. Then you have to see that there are 4 assumptions are hidden. Some like so. You have 9 groups, but 5 parameters. That means 4 hidden assumptions are made when you estimate this regression. So you have to find it out by yourself. But anyhow, it's working. It's working. But the problem is whether that assumption is correct or not. Okay, I did it. Right, so as you can see, the main assumptions are these two groups are the same. Not the same. So So the difference between these two groups are gamma 1 and gamma 2. That's the same across this, right? So difference in differences are the same, right? So difference in differences are 0. So, and this is the reference group. We dropped T and J, T from here and J from here. So that is the reference group absorbed into the intercept. But we are making some assumptions like in the differences, right? Differences are the same across this dimension, all right? So hard to say that. Just do the algebra. So interpretation is beta 1 is the difference between sedan and truck for Japanese cars, right? So beta is this difference, but at the same time, beta is the difference between sedan and truck for German cars or American cars. So the sedan premium is the same for American or German or Japanese cars. So does not matter where the cars are made, the sedan premium is the same. That's the assumption hidden here. And another assumption is like beta, SUV premium over truck is beta 2. But that does not depend on nationality, where it's made. Okay. Similarly, gamma is American premium over Japanese cars. American car premium over Japanese cars is gamma, but that is the same for sedan, SUV, truck. Okay? So, and same thing for gamma 2. So I said already 4 assumptions. Beta 1 same across, beta 2 same across groups, and gamma 1 same across groups, gamma 2 same across groups. That is 4 hidden assumptions as I mentioned here, right? Well, you should be able to understand that. So, and yeah, exactly. That's excuse me, allergy. So that's what I'm saying here. And part B, here same, like here the multicollinearity without intercept coming from S plus U plus T equals A plus G plus J. So this is the multicollinearity problem. So we have to drop one of them. Like you don't need to drop 2 because already you dropped intercept. So now you have to drop one more. So and then the interpretation is more complicated. You have to see. It's your practice. I will leave it to your practice. So you can try what kind of assumptions are made and what is the interpretations of those parameters. If, for example, if you drop J or drop T, so you should be able to do that. More complicated, annoying problems. Now the multicollinearity is coming from this, right? So S and SA, SG, SJ cannot coexist in one equation. So you have to drop one of the 4 variables. So suppose you drop this, but you may drop this. It doesn't matter. Just drop one of the 4. Then you have these 7 parameters. That means there are 2 assumptions are hidden. 2 assumptions are hidden. So you have to find it out. And also you have to find what are the interpretations and what's this intercept implies. So it's your practice, right? Fine. Equation is too long, so let's go back. I'm sorry for the crazy equation. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 parameters. So that means we have 9 groups but 11 parameters. That means there are at least 2 multicollinearity, but there could be more than 2. Let me see. like SA plus UA plus TA equals A, and SG plus UG plus TG equals G. So these are two multicollinearity. Let me see if that's correct. Yes, there are two multicollinearity you can find. So again, you have to drop one variable from each group. Drop one among these four, and another one from these four. Then you will have 9 parameters. So there should be one-to-one mapping, right? So now it's your practice to find the interpretation, to find the one-to-one mapping between the parameters and the groups. So how you interpret them. So additional exercise, if you're interested. Does it have multicollinearity or not? And does it have multicollinearity or not? So try this and try to interpret the parameters. It will be an interesting exercise. Good luck. By the way, as you can see, this is really practical issue, and you will encounter this kind of data in your research. So make sure you understand what's going on. Okay, bye.